大家好，我们的组名是不要违背我们的旨意。我是张志毅。We are Group 14. Our topic is Intelligent Clothing Tagging and Pairing System. Let's briefly introduce our system. We found that most online outfit generators simply create a full look based on style, while sometimes we don't have the suggested clothes in our closet. So we want to develop a more user-centered system, which can recommend clothes from the user's closet. Our intelligent clothing tagging and pairing system will recommend a compatible bottom based on a given top. The capability is considered by the clothing attributes, such as fabric, color, style, and so on. Next, I'm going to introduce one relevant work, Clothes Recommendation System based on Style Recognition by Chow. In this work, it defines clothing style as a form of emotion, and it builds a style space using a dimension emotion model. The system relies on low and mid-level features, such as clothing attributes and color harmony. It uses handcrafted datasets and style score functions to recommend outfits aligned with the desired emotional tone. In contrast, our project doesn't use handcrafted datasets. Instead, we train our model using a Polyword dataset, which contains real-world popular outfit combinations. Based on multi-label attribute compatibility, our system gets to learn what combinations of clothing tags are commonly paired. As a result, our system can discover stylish matches and recommend more trend-aligned outfits. Furthermore, our system improves usability by matching clothes in users' closets. And we use MLP, which is multi-layer perceptron, to design our matching model. Multi-layer perceptron is a type of feed-forward neural network. It consists of multiple fully connected layers. Each layer performs a weighted sum of its input, followed by a nonlinear activation function, such as ReLU or sigmoid. This nonlinearity allows the network to learn complex patterns and relationships in the data. Multi-layer perceptron is widely used for.
Let me introduce the datasets we used for training our labeling models. We utilize two main datasets. Deep Fashion dataset. We use the category and attribute prediction subset of Deep Fashion, which includes approximately 200,000 clothing images labeled with 1,000 attributes, excluding color. We train a multi-label attribute classification model using this data, enabling the system to take uploaded items with fine-grained attributes such as fabric, neckline, and style. Another dataset is DigiColor color classification dataset. To provide color information, we use this cargo dataset that contains color-labeled clothing images. We train a color prediction model to complement the attributes tag with accurate color detection, enabling automatic metadata completion without manually defining color categories. For training our outfit compatibility model, we use a curated version of Polyword dataset, known as the Clint Maryland dataset. This dataset includes predefined top-bottom outfit pairs, making it ideal for learning how to match clothes. However, instead of using this combination directly, we applied our own filtering pipeline to enhance the data quality. This custom curation process allows us to modernize the dataset and ensure that only relevant and compatible combinations are kept for training. This slide explains how we cleaned the good match dataset. First, we removed full-body outfits like dresses and jumpsuits to focus only on valid top-bottom pairs. Then, we used our attribute prediction model to tag each item with features like texture and shape. Based on these tags, we manually filtered out outdated or weird combinations. For example, a sporty hoodie paired with formal trousers. By doing this, we ensured that all the samples in our match dataset are truly compatible and modern. Here, we show how we built a negative dataset. Outfits and should not go together. First, we use the attribute model to identify conflicting pairs, like long trench coats with hard pants. Then we use the color model to detect color clashes. For example, neon orange with bright green. This mismatch rules help us create a strong negative set, and also allowed us to refine our positive state by removing borderline or ambiguous pairs. This is our training process overview. Attributes label model. This model is designed to predict the fine-grained attributes of clothing items, such as sleeve type, neckline, fabric, and cut. It was trained on the deep Bayesian dataset, which includes 1,000 well-defined attributes. We use the ResNet 1.8 architecture, and the final fully connected layer is replaced with a 1,000 dimensional output, each dimension representing one attribute. Each output value is passed through a sigmoid function, converting the raw score into a probability between 0 and 1. And this model is color label model. It's trained in almost the same way as previous attribute model. And to train these two label models, we mainly rely on two components: binary cross entropy loss and the Eden optimizer. And BSE loss is commonly used in multi-label classification tasks. It measures the difference between the predicted probability and the ground truth for each label. Each label is treated as an independent binary classification. The sigmoid function transforms the model's raw output into a probability between 0 and 1, and BSE loss computes how far of that probability is from the correct answer. BSE is particularly used for here because clothing items may have multiple attributes or multiple colors, and each label must be predicted independently. An Eden optimizer is used to update the model weight during training. It is known for its ability to adaptively adjust the learning rate for each parameter by maintaining two moving averages. Eden is especially effective for high-dimensional and sparse data, like our attribute and color prediction tasks, where many outputs are often near zero. It helps the model converge faster and more stably than traditional optimizers like SGD. This slide shows an actual example of how our label models work. The image on the left is blue shirt sleeve top. The attribute label model predicted several relevant texts like sleeve, crew neck, shirt, and cartoon, each with a score showing the strength of prediction. The color label model correctly predicted blue with a confidence of 0.996 and very low values for all other colors.
Next, I will introduce our baseline matching model. We designed our baseline matching model using multi-layer perceptron. We designed three fully connected layers with value and dropout. The input is the feature vectors of the top, and the output is the predicted match feature vectors of the bottom. The baseline model is trained only on the matched pairs dataset. During training, we use binary cross-entropy loss to compute each label's loss, and we use focal loss to balance each attribute. This formula shows how we calculate focal loss. The alpha value is calculated by the frequency of each attribute and is used to increase the loss contribution of minority classes.
Here is the core model of our main approach. First, let's start with the input form. We combine the two types of embedding. One is attribute embedding. These are extracted by the pre-trained model that we mentioned earlier, and which takes various thematic attributes. And the second one is a color embedding, which shows the color relating information into a 12-dimensional vector. And then we get a high-dimensional feature vector that represents the clothing item. Next, let's look at the model architecture. We use a multi-layer perception to process the pair of clothing items. Then the input is the combination of the two feature factors, so the total input size is 2 times the number of the label. And the model output a single scalar value representing the compatibility score for this clothing pair. And importantly, this is formulated as a binary classification problem, and the model learns to predict whether the pair is compatible or not compatible. And this design allows the model to capture both linear and nonlinear relationship between the combined feature of the two clothing items. And for the datasets, compatible pair are labeled as 1, and incompatible pair are labeled as 0. Then we use the loss function to handle the class imbalance in the dataset. By using the positive class-wide can help the model give more importance to minority classic sample and penalize more when it misclassify them. And we use an optimizer with a learning rate that we have experimentally turned. And in addition, we split the data to avoid overfitting. Now let's take a look at our evaluation results, comparing the baseline method with our main approach. And in this test, we evaluate how well the model can recommend the correct button closing from 40 candidates for each tab using the polyvore data. And the baseline relies on the simple attribute prediction for basic matching, and the main approach using a binary classification MLP model, and which learn compatibility directly from the data. On the right, you can see the comparison table, which shows several evaluation metrics. And in the line plot, the orange line represents the main approach, and you can see that it generally ranks lower across different tabs. Here are some key results. Our main approach achieved a lower average rank. This indicates that the correct buttons are ranked higher, closer to the top position. The top 5 accuracy also improved. And additionally, the binary classification NLP model delivers more stable performance with fewer extreme outliers, as shown in the ranking plot. In short, the compatibility-based MLP model is clearly more effective for the closing pairing test. It learns better representation than simple attribute prediction.
Now, let me walk you through the result and analysis section. This part is all about understanding how well our model performs, especially from the perspective of users. So, to evaluate our outfit recommendation model, we designed a simple survey. The idea was to see how people actually feel about the outfits generated by our model. We gave them 3 different tabs, and for each tab, they had to give a score to each of the 4 different button options. The first option is the recommendation from our model, and the second is the original matching from the training dataset. Others are random combinations. Let's take a look at the results. There are 2 key points I'd like to highlight. First, our data shows that the model's recommendations generally scored higher than the random combinations, and in many cases, they even outperformed the original parents from the training dataset. For example, Type 1 and Type 3 are great examples of this. This suggests that our model can discover some more appealing parents that users might prefer. Second, our model assigns a score to each top-bottom pair during inference. A positive score means a good match, and a negative score indicates a poor match. When we checked the survey results, this was confirmed. Outfits with scores above 0 were more liked by the participants, while those with negative scores were generally less preferred. Finally, we've prepared 2 charts to make the result clear. First, this bar chart shows the average rating for each type of pairing. As you can see, the model's recommendations, just the green bars, had the highest scores, followed by the original pairings, the orange ones, and the random combination scored the lowest. Then here's the box plot. This shows the distribution of scores for all the responses. What stands out here is that the model's recommendations not only scored higher, but also had a more consistent range, while the random combinations had lower and more scattered scores. This tells us that the model's recommendations are not only better, but also more stable. So in summary, our model doesn't just generate reasonable outfit combinations. It can actually outperform the original parents from the training data in some cases. Let's move on to the demo part. We select this pink top. The system will not suggest these bright green shorts because they clash in color. Here is the result. Also, every tab will get different button recommendations based on its style and color, so when you click on a different tab, the recommended buttons will update accordingly. This is the end of our presentation. Thanks for listening.